When you are done and you bow, I can come back.
Wow, I stole all the best bits, Indy. Well, thank you very much. Thanks to Indy for a very generous introduction, which is probably unwarranted. And also thank you to every one of you for coming here. I appreciate it. I thank you all sincerely for coming, and I'd like to also recognise the university for actually putting on this series of lectures, which I think is a nice new initiative. It gives a chance for academics to, when reaching this professorial milestone, to explain what motivates them and hopefully show that they're, relatively normal people. I'd also like to quickly thank my family members for coming, either across the Pennines or across the North Sea. It's not an easy journey to do, so thank you very much for being here. Sorry, I've had bronchitis recently. So yeah, I'd like to just sort of say this is a particularly fulfilling milestone for me, because I am the first member of my immediate family to actually pursue an undergraduate degree, let alone postgraduate study or an academic career. So every step of the way has been a bit of a fresh challenge for me. But as a family, what we may have lacked in experience, we've compensated with support and lots of leg pulling. So, right, so the title, I should have said it, shouldn't I? So Utilita ex machina, what does that mean? It just means help from a machine. Right, so having claimed that I'm the first person to go to university from the family, sort of trying to lean on my working class roots, what am I doing picking a pretentious Latin title? Where does this come from? So I promised I would explain all. It comes from this guy here. So my in-laws are laughing because this is a close friend of theirs. So this is a guy called Sandro. He's a geologist, just like my father-in-law, and he's the director of a geological observatory in the Apennine Mountains in Italy. He's a very funny guy, always worth talking to. And this is his garage. So like the daughter's workshop within which you can find many helpful and usually dangerous machines. He'll always say, if you've got a problem, go and get help from a machine. So I thought I would nick that one because we were there over Christmas, and it seemed like a good title in advance. Sorry. Right, so help with what, though, you may ask? Right, so this slide is used and abused by just about everybody in our field. So this is a student dressed, clearly he was a Durham graduate, poking their nose into the workings of the universe. So, God has given them this wonderful world to live in and to be ignorant of how it came about, but they're sticking their nose into cosmic affairs and trying to figure out how it all works. And that's pretty much what I do, not being content with just sort of living in the world. You want to know how it works. That's basically the lot of the physicist, isn't it? So what kind of questions might we want to ask? And what kind of questions does my research try to entail? Well, I'm kind of preaching to the choir here because you're all, nearly everyone in here is an astronomer of some description. So yeah, don't fall asleep. But we can ask questions like, what is the universe made of? That's a pretty fundamental one. What did the universe look like when it was a baby, billions of years ago? Where do the galaxies and the stars within the galaxies and the planets that orbit around those stars come from? Why is there such diversity amongst the galaxies? Because the galaxies themselves don't all look the same. They all look very different. They have a range of masses. And what might the universe look like in the future? And if you want the answer to that question, seek out Jaime. That's his expertise. So go and ask him. Don't ask me. It'll look boring, though, is the answer, I think. So, right. So first thing to do is put up a nice, beautiful picture of a galaxy. This is a real one. It's not one I simulated. We're not quite this good yet. So this is a beautiful spiral galaxy, M51 maybe. The observers will correct me if so. One of the things I like to come back to occasionally is to look at these things. These are the conspicuous and very elaborate icing on the cosmic cake. And it's a constant source of wonder to me that our universe produces structures like this, right? I mean, the universe could have had any set of physical laws in it that could have produced any old sort of thing. And this is what the particular initial conditions of our universe, when coupled to all of the physical laws that govern it, this is what it produces. I think this is as beautiful as just about anything in the natural world, be it the flora or fauna we find on the Earth. It's a very visually spectacular thing for us to try to understand. And it's also a source of wonder to me that as a species, humankind, we've been able to piece together a large fraction of the story of where these things come from and where they're going. I think it's one of humankind's most spectacular intellectual achievements. So I'm just going to show you two more pictures of galaxies. Firstly, even I know what this one is. This is M82, nearby starburst dwarf galaxy. I show this because it's got these spectacular winds. So there's a starburst going on in the middle, lots of young stars being born and dying very quickly, and that forces this this jet or this wind of very hot, very high velocity gas out into the nearby cosmos, and that's regulating the growth of or the formation of more stars in this galaxy. And at the other end of the spectrum, this is a galaxy that's many, many times more massive, so maybe 1,000 times more massive than the one we just looked at. And this one's dead completely. You see, it's not blue, it's yellow, or red. It's not forming any new stars at the moment. And in the middle of here, there's a 4 billion solar mass black hole that's secreting tiny amounts of gas that are still present within the galaxy, and it's shooting these huge energetic jets of plasma at an appreciable fraction of the speed of light out into its environment. And that's also causing this galaxy to basically shut itself down. It's put itself on a diet. And we'll see these two galaxies come up again later on, and I'll explain why these two are particularly interesting for the sake of my modeling. Okay, so before we get into all of that, I wanted to talk a little bit, go off on a little bit of a ranty aside about the role for mathematical and computational modeling, because as Indy explained, most of what I do involves the use of large computers. So if we cast our mind back many, many years, a couple of millennia back, this was the leading authority on gravity. So this is Aristotle, one of the world's greatest thinkers, wrote books about just about everything. And he said the speed at which objects fall is proportional to their weight. And for about 1,800 years, this was the prevailing wisdom, which doesn't speak volumes for our curiosity as a species. So I might be a theorist, but I occasionally conduct experiments. So thank you to Renske for preparing this. Right, so you all know what's going to come, right? This is heavier. This is 9 times as heavy as this one, so this one's going to fall faster, of course, okay? Let's do the experiment. 1,800 years. This guy was the leading authority. So there's a lesson there. Now I'm a professor, I get to profess. I'm going to profess, don't listen to authority. Go and do your own experiments. Oh, should have done that before. Right, so the reason, after 1,800 years this sort of idea came to an end was because of this guy, or partially because of this guy. So Simon Stavin, incidentally, he was one of Leiden University's first students, but he never graduated. And he did the experiment that Galileo is sort of known for, even though it's not clear that Galileo actually did it. Sorry, I'm getting thirsty. And so he went to Delft, just down the road from Leiden, and dropped lead balls of varying weight from the new church tower in Delft, not that new. And he showed that basically everything falls at the same speed as long as it doesn't have an appreciable air resistance. So this was a pivotal moment, not just for proving that Aristotle was wrong, but it established experiment as the primary authority in establishing our scientific understanding. So stop listening to people, go and do your own experiments and prove it to yourself what's going on. Okay, so it was this guy who explained why these very different weight lead balls fall at the same speed, and it was a big intellectual leap to make it. And I'll just point out he's from Lincolnshire, so there's cosmologists besides myself who come from Lincolnshire. Right, so I tried to not put too many equations in here, but here's a couple of good ones. So we all know Newton's second law of motion: the net force on a body is equal to the rate of change of its momentum, or if you want in a simpler way, its mass times its acceleration. So that was something he came up with, by looking and doing experiments on Earth. That's his own lived experience. But he also came up with an idea, and there's an idea that came about from trying to understand the laws that Kepler had come up with. So he actually looked at the rate at which planets was around the sun, and he postulated this form of the gravitational law, right? So the gravitational force between two objects is proportional to the product of their masses and the square of the distance between them. So you can see what happens if you set these two forces equal to one another. So GMM over R squared equal to MA. This M and this M cancel out, right? And that's the mass of the beanbags. right? So the acceleration doesn't depend on the mass of the beanbag. It matters only what's the mass of the Earth and how big the Earth is. So we made, provided the explanation for why our intuitive ideas, and that's basically what Aristotle was coming up with. It was just intuition, wasn't it? He showed that that was wrong. So that was an important intellectual leap because it linked experiments of the motion of objects on Earth to the observed motion of the cosmos, or objects within the cosmos, and he did it using the language of maths. So that's a very important step to have taken. Right, so that's fine. Okay, you can do that for a two-body problem. You've got the beanbag and the Earth, or a planet whizzing around the sun. But the universe has many more bodies in it. So if you want to understand the evolution of the whole universe, you're going to have to take the next step. Now, anyone who's got a Netflix subscription will know dehydrate. The three-body, that's a really niche joke, isn't it? The three-body problem has no analytic solution, right? So if I start this three-body thing off, it looks fairly simple, but pretty soon it's going to get chaotic, and we're going to have no hope of following this with analytics. So the only way we're able to predict this motion at all is by applying the laws of motion iteratively. So we apply them, move everything a little bit, reapply them again, and just keep computing iteratively and going on and on and on. So that's a three-body problem. So let's have a look what happens when we have to go to an n-body problem. So here's a video I made earlier. I didn't make that last one, but I did make this one. Right, so this is Eagle that Indy introduced earlier. So I guess the main part of my life's work. So here we might have, several 100 million particles instead of 3. And the initial conditions of the universe have been imprinted on this to start with, so we know those very well from studying the cosmic microwave background. And here we're just including the dark matter, so there's no gas or stars or anything like that here. It's all just the dark matter that we think dominates the matter content of the universe. And we're basically just applying Newton's laws over and over again, iteratively, until we form this spectacularly rich... just looking at my clock on here, and it's completely wrong. Okay, got this, this beautiful structure on here, right? So, what I would say here, coming back to the point I made earlier, is that we're able to make this amazing leap about trying to understand why the structure of the universe is the way it is. And the real key point of this story, I think that this is a bit that blows my mind about us as a species, is that we think that these initial conditions come about because of quantum mechanical effects in the very, very earliest instances of the universe, right? So we have this process that we think was called inflation, where the size of the universe grew by some ludicrous number of orders of magnitude in the blink of an eye. And that inflated these quantum mechanical fluctuations up to macroscopic scales and imprinted a very specific set of fluctuation wavelengths onto the universe. And if you couple that initial condition with the laws of gravity, this is what you end up with, right? So this basically explains why galaxies are distributed in our universe the way they are, and why the structure of dark matter is the way it is. So I think this is one of the single most important accomplishments of humanity, right? I think this ranks up alongside understanding how the human body works or producing artworks like the Mona Lisa. I think this is comparable. This is a really amazing story. Right, but I'm getting ahead of myself, so I'm supposed to be slightly autobiographical. So we'll get to that in a second. But first I want to give some perspective that's probably completely unneeded for 90% of the audience. Right, but let's just zoom out from the Earth to give ourselves a sense of what a galaxy is and how many galaxies there are. So we're zooming away from Earth now. We're going to go past the Moon. Gratuitous movie, you've got to include them, haven't you, right? So we're going to go past the Sun here. And we'll see that the Sun's got lots of neighbours if we zoom out far enough. So these are the nearby stars like Proxima Centauri. And if we hit the gas and go, warp speed, we'll suddenly see that the Sun is completely uninteresting, right? There are tens of billions of stars like the Sun in our galaxy. And as we zoom out and out and out, we realise the Sun just lives in a completely innocuous part of our galaxy, somewhere sort of 8 kiloparsecs away from the centre. So we're not in the centre, we're not at the edge, we're somewhere in the middle. And as we zoom away from the galaxy, we see, wow, the galaxy itself is even not very special, right? So here's our neighbouring galaxies in the local group. And once again, we're going to hit the gas and zoom out and realise, there's tens of billions of galaxies as well. So this is how you get your sense that you are completely inconsequential in the universe. But it also shows you that, this is an amazing problem for us to be able to attack, right? Not only do we understand a lot about our own galaxy, we understand a lot about why the galaxies look the way they do and why they're distributed the way that they are. So let's zoom back down to Earth. And I'll tell you something about, which I'm much more familiar with than the distribution of galaxies. And that's where I was born, right? So here comes the autobiography. So as Indy said, I was born in Lincoln, home to the finest piece of architecture in the United Kingdom. So the first job I wanted was to become some sort of evangelist for the cathedral, as like a lay member. I was kind of beaten to it by John Ruskin, so the Victorian polymath. He once said that Lincoln Cathedral is out and out the most precious piece of architecture in the British Isles and worth any two other cathedrals we have. And he said this even before Liverpool's cathedrals were built, so he wasn't on about getting rid of those. He was going to give up Ely and Salisbury or something like that, so he really likes it. And I was lucky to live about a mile in that direction into the page, so about there if you look hard enough. And my dad still lives there, so so Lincoln's got the best building in the world in it. Now this building, I'm not bringing it up just to brag about Lincoln. This building was once home to arguably the first Western cosmologist, so maybe it was in the water or something, I don't know, that I was going to get into this game. But 400 years before Newton came along, Robert Grosseteste, or Robert Bighead, so make your own jokes, was Bishop of Lincoln, so 1235 to 1258. And he was arguably the first person to argue that you can try to understand the universe in terms of the laws of mathematics. So he thought that you could do everything in terms of geometry. So there's a quote in one of his works that all reality in the universe can be expressed in lines, figures, and angles. That's basically what we do, isn't it, as scientists these days. And interestingly, he wrote a scientific document called De Luce, which described light as an infinitely small particle that may be the origin of matter, right? So this is like 800 years before quantum theory came about. He already had this idea, so he beat Einstein to it as well as Newton. So fascinating guy, and when I've got more time, I'm gonna get a statue to this guy built in Lincoln. That's gonna be my job. Right, but anyway, I didn't want to start off as a cosmologist, despite having this local inspiration. The first thing I wanted to do was become an organic chemist. The reason this came about was because when I was about 5 or 6, I discovered that there was a wealth of complex organic compounds available to me in the kitchen in the form of things like salad cream, vinegar, mustard. And I would get jam jars, fill them up with varying ratios of these horrible gluggy things, mix them up and leave them on the kitchen windowsill, presumably for UV catalysis purposes, I don't know. And I would go away, play Nintendo, football or whatever. And I would come back and I would find that invariably these horrible brown sludges had turned into something that looked like these. And it was months later, after doing lots of experimentation to try to understand which mix of salad cream and vinegar gives you orange or green, when I discovered that family members had been pouring it down the sink and filling it up with food colouring. So I really wanted to stick with the organic chemistry for a long time. And even got the goggles ready for it, right? So do the maths, right? But anyway, right. So I really enjoyed science at school. I was lucky to have good science teachers, so I made the decision to pursue science as an undergraduate. But I just wanted to point out, before getting into all of that, I had a taste of the real world, and that was what has persuaded me to stay here, despite everything. And I had some really tough jobs. So one of the things I used to do was go and work for my cousin's construction company, and he would smuggle me onto sites that were illegal for someone of my age to be, and have me sort of crawling up pipes and getting into nooks and crannies that bigger, gruftier blokes couldn't get to. So I spent 2 summers in this building here, which is the pump house at High Marnham Power Station, which is now decommissioned, nothing to do with me, repairing the pumps that feed water to these cooling towers. And these pumps were 72-inch diameter, so they're absolutely huge. And I swear I've never done a harder day's work in my life than spending time in that pump house. It was horrible. Just before going to university, I had got a job closer to home, and it was really nice because I was working with my dad. We worked in this building here, so this is what's sort of known in Lincoln as the Forge. So it's a big engineering site that had made automotive and aerospace components. And I was sort of finishing off mining components that Dad was also working on. So it was really nice. We spent the summer working together. I now understand why British industry has fallen to bits, because there's a lot of japing around goes on in these factories. But really, it was sort of the near-death experiences that I repeatedly had doing these jobs that persuaded me that an office was the best place to conduct your career. So I got out and decided, yeah, I should go and spend 8 years in a town with a mediocre cathedral. So I moved myself up to Durham, as Indy said. So I stayed 4 years doing my undergraduate degree, and then another 4 as a PhD student. And it was a great place to learn the craft of astronomy. As you all know, there's a very big astronomy group there that we're now trying to crush from across the Pennines. And once I was up there, I got very quickly influenced by some characters that will be known to many of the people in the room. So already, I think one of the first lecturers I came across was this guy who we'll sort of know and love. Poor old Richard, who passed away at the start of last year. A very untimely end to a brilliant career. So Richard used to do a course. I don't know if John, did you do the motorsports course?
Not quite.
Awesome. He would just sit us down and make us watch videos of rallies, and then at the end sort of do an exam on it. But it was great. We did a couple of lectures of classical mechanics. Everyone passed with flying colours because Richard was very kind with his marking. And then the next course on this elective module was done by this guy, whose name's already come up once. So he did an introduction to cosmology, and it started with the Mazaros effect. Right, for those of you who are cosmologists, you'll know what that is. If you don't know what it is, you don't need to know. But it's not the sort of thing that needs to be taught to first-year undergraduates who are just rocked up and are all bright-eyed and bushy-tailed. And it got harder from there. So most of us failed. And it put me off doing astronomy for about 2 years, actually. Until in the 3rd year, I encountered this guy, Sean Cole. And so he taught the cosmology module in the 3rd year, so he was kind of their version of Jaime. And that module persuaded me beyond any doubt that I wanted to work on theoretical astrophysics and cosmology. I was just hooked on it. Sean was an absolutely fantastic lecturer. But the course also made it clear that there was a lot of frontier questions in the field that still needed to be addressed. And it was kind of clear from the outset there that those questions could only really be addressed with numerical models. And so I begged Sean, for the following year to supervise my master's project, and he agreed to do it. It's one of the best projects I've ever done, actually. I still think it's amongst the best work I've done. And I desperately wanted him to be my PhD supervisor. Unfortunately, he said, at the end of that, I'm not taking anyone on this year. You'll have to go and work with the boss. So, okay. So I ended up working with Carlos, who, as we all know, is one of the world's most highly cited physical scientists. So it wasn't the worst thing in the world to have to go and work with him. But so Sean got to escape from me. So this was me after Sean had finished with me and before Carlos had got his hands on me. Still looking fairly healthy and dark-haired at that point. And the key thing was, at this time, the Institute for Computational Cosmology had just opened, right? So I think, well, we'll see in a moment. In fact, we'll see now. It was opened by Mr. Blair in 2003, so just before I started my PhD. So it was open just in time for me to actually do my master's project in there. So my office was just behind this thing. And so as well as Carlos, I was supervised by Adrian Jenkins, who I'll superimpose on Tony. So Adrian's kind of like the yin to Carlos's yang, right? I mean, Carlos is a very bombastic character, and Adrian's like very quiet and taciturn and detail-oriented. So they were a good pairing to work with. And just while I'm here, this is a slight tangent, but I'm going to bring this up since her office was just here. One of the other people who really influenced me in those days was Lydia Heck, who I've always maintained was the smartest person in the building. She had a PhD in quantum mechanics, and she ran the computers. So she was the mother of Cosmo. She was kind of probably inappropriately called at times, but Lydia taught me so much and had me in the machine room more time than I probably spent in the office. And it's probably thanks to her that the guys in ITS now suffer. So you can blame Lydia for everything I inflict on you. I'm sorry about that, guys. But this was a fantastic place to work. The building was set up perfectly for collaboration, and I had great days working there. I really enjoyed it. Okay, so I want to put up this plot next, sort of slightly gratuitously, because it's from the annual review that I published last year. But the reason I wanted to show this is that it kind of gives you a sense of why this field has taken so long to mature. I think the first simulations of the kind that I'm interested in started in the early 90s, and it really took until, well, I'd argue 2015 for us to be able to make fairly realistic sorts of simulations. And it's because we've got this terrible problem with scales in astrophysics. So very small things tend to percolate up the food chain and influence the very big things. And also the very big sort of structure of the universe, the large-scale structure of the universe, also has an influence on the galaxies down the food chain. So we can only numerically simulate part of the dynamic range at any one time. This thing's ridiculous, isn't it? So we tend to focus all of our computing power into sort of this region, and then we have to treat everything up here with simplified treatments. And those simplified treatments, it turns out, end up dominating the uncertainty and the outcomes of the simulations. So that's sort of why we're still sort of not at the complete answer yet. We can never hope to do ab initio the whole problem. Okay, so once Carlos had got his hands on me as a new student, I was looking for a problem to work on. I should say, well, I'll go back one. So just about the time I started, everybody was working on something called the Millennium Simulation, which I'm sure most people have heard of. So it's a very big dark matter-only simulation designed to study why galaxies are distributed in the cosmos the way they are, and why dark matter halos have the properties that they do. And this was, big deal. We had a big meeting in Germany about it just after I started. Newsnight came, Jeremy Paxman narrated a whole piece about it. It was really big news. It was like front page of some of the broadsheets at the time. And I decided I didn't want to work on it, despite it being the latest big thing. And it's because I thought it was boring. It just had dark matter in it, and I wasn't interested in that. I wanted to study all of this fun stuff. So I kind of became a bit of a renegade from day one. And the reason I was able to do that is because of this guy, who I've ended up never actually working with, but he was hugely influential for the early part of my career. So he was a sort of very quiet and shy postdoc from Japan, Takashi Okamoto. So he just arrived in Durham as I was starting my PhD. And it was timed perfectly because he wrote this paper that proved to be extremely influential. And anyone who sort of worked on owls and eagle afterwards will, you sort of owe a lot of our results to what Takashi came out with. So he simulated the same galaxy 3 times. He was one of the first people to have a complete version of Gadget with all of the bells and whistles in, so it had like gas cooling and stellar evolution, feedback from supernovae, etc. And he showed that the way you implement that feedback energy has a huge bearing on the outcome of what the galaxy looks like. And as we all know, this has sort of been what has influenced a lot of what has come in the last decade or so in our field. And he got there back in 2005. And I think this paper, it's a very well-cited paper, but I still think he doesn't get the credit he deserves for this. And so I spent a lot of time nagging Takashi and basically having him explain everything to me, which he did very patiently. He was very generous with his time. And I learned a huge amount from him. And I was therefore very well prepared when a very good opportunity came along. So Indy mentioned this thing, Gimmick. So just as I sort of was cutting my teeth looking at some of Takashi's simulations, we got a big opportunity to get some computing time through a European scheme, and it ended up giving us time in Edinburgh and Durham. And we used it to run this thing called Gimmick. Now, this box here is actually that Millennium simulation that I didn't want to work on, right? So this is a big volume. This is 500 megaparsecs on a side, so 1.5 million light years across. So it's supposed to be a reasonably representative chunk of the universe. Now, we could never hope to simulate all of this volume with all the bells and whistles needed to form a galaxy that looks like this. So we did something I think was quite clever. We cut out a number of regions that are selected to be environmentally diverse, and they were still quite big, right? So they're sort of like 5 megaparsecs in radius. And we simulated those with the requisite resolution to make galaxies. And it's such a good idea. This is what Jemima is now doing for her PhD in a similar way. So I was well prepared to sort of grasp the opportunity when this came along and sort of said, I want to lead this, I want to be involved in this. So I did. I ended up writing the lead paper for it. So Ian also got involved with this soon after, as did Andrea. And as you can see, there's some pretty big names on here, and I can tell you that getting this paper out the door was not an easy task. But when it did go out the door, it was in very good shape. So it was nice to be able to work with some of these luminaries. So one of the big results that came out of it was that we could basically make the cosmic star formation rate density reasonably realistically, right? So this is a plot that's showing you, so redshift here, this is our way of measuring time in the universe. So here's the corresponding time, the age of the universe along the top axis. And this sort of Byzantine quantity here is just how many stars you're making per unit volume of the universe per year, right? So if you're higher on this, basically the universe is making more stars. So you can see the observers go out and measure this, all these crosses are observational measurements, and you can see it kind of goes up, peaks, and then falls down again. So the universe stops making stars after about redshift 2 or so. So it's worth noting this top axis, right? Most of cosmic history is around here. This is a very wasteful plot, but this is the way observers do it. Idiots. So this was quite a big deal at the time. We got this history fairly well. The problem is that we put all of the stars in the wrong galaxies. So this is the stellar mass function. So this is the mass of galaxies here on a log scale. So these are tiny little galaxies, and these are really big, monstrous galaxies up here. And this quantity here is just telling you, again, how many galaxies you have per interval in this mass scale per unit volume of the universe. So at the top, it means you've got a lot of galaxies, and down the bottom, you've got not many. And again, these circles are the observational measurements that the observers tell us from surveys is how the universe looks. And, well, you can just take this black curve as the answer from the simulation. So I'll call him out. Carlos actually didn't want us to publish this. He said, no, everyone will think we're idiots. I said, well, we've got to publish it because we are idiots. We clearly don't know what we're doing, and there's a target for the future. So fortunately, some of the other big wigs agreed with me and said, yeah, we should go and publish this. So we did. And I think it was an important milestone for the field that we admitted that we had a big problem. Now, the nice thing was, at least, we got kind of the right number of galaxies here, which is where the Milky Way lives on this plot. So we were able to still do a lot of interesting science with with Milky Way-like galaxies, which is where most of us are interested anyway. So it wasn't a dead loss that this plot looked quite poor. And so one of the things I got into working on and have never really let go of since, as John will tell you, is looking at diffuse X-ray emission from the halos of these galaxies. So just to sort of give you some context to this, so back in the early 90s, Carlos wrote a paper with Simon White. It's a very influential paper, very well cited, 3,000 or so citations. And that analytic model made a very bold prediction, very unambiguous, that every galaxy like the Milky Way should be enveloped in a hot halo of gas that should be very readily detected in X-rays. And around the early 90s, ROSAT went up. So this was one of the first X-ray satellites dedicated to astronomy rather than finding nuclear weapons. And people went and looked. In fact, Andrew Benson, famously Carlos's favorite student from Lincoln. So Andrew's from Highcombe. But he sounds Californian these days. He's been in the US for a long time. So he wrote this paper and went looking for these halos, and they found none of them. So they basically put upper limits that were completely incompatible with the theory. So we wanted to know why. And we thought, well, this is the perfect time to do it, because at around this time, a very quiet, unassuming postdoc had arrived in Durham from Canada. He's not here, so I can be rude about him. It's great. Yeah, so Ian turned up, and believe it or not, Ian and I hit it off straight away. We used to sort of drink a lot of coffee together in Durham. Now he doesn't talk to me anymore. He does. He gossips with me, but we don't talk as much science as we used to. But before Ian became like this, angry cosmologist who doesn't like galaxies anymore, he was an expert on modelling the hot intracluster plasma. So he knew all about how to turn properties of gas into X-ray emission. So Ian taught me how to basically couple the simulations to the APEC tables that X-ray astronomers use. So we know, as a function of temperature, how much radiative cooling you should get from the gas, and that's basically the number of X-ray photons that you would count with a satellite like ROSAT. And so, I wasn't content with just making a prediction of redshift 0. I was like, oh, let's go make a movie. So we ran a simulation of a galaxy, and the red here shows you the cold gas that will end up making the galaxy disk. And the blue actually shows you what the simulation predicts is the X-ray emission. So I apologize for how ropey this is compared to modern standards, but this was like really eye-opening to me when we made this movie, because you can see, wow, there is an X-ray halo, it's there. But then as the simulation ticks on and on and on, it starts to disappear, right? It gets fainter and fainter, and you occasionally see flare-ups when another galaxy sort of whizzes by and causes a shock in the gas. But by the present day, when you've just got a quiescent spiral galaxy, there's hardly anything there. So this was like, wow, we've solved the problem, it was great. So you can go and then look at a population of galaxies and build plots that show the X-ray scaling relations and compare them with what ROSAT does tell you you've got. And so this was sort of one of the big first successes of GIMIC, was that we made a plot of the brightness of the galaxy, just in terms of the optical brightness of the stars, and then plotted as a function of that the brightness of the hot halo that you get from the X-rays. So every black dot on here is a galaxy in the simulation, and all of the coloured points are observational measurements. And I think you can agree, you don't need to do any statistics there. It was a pretty good match. So we didn't have this like glaring error that we thought we'd got when we used Carlos's theory. So the nice thing is that the simulation obviously then gives you a way of trying to understand, well, what did they do wrong? Because the simulation gives you all of the properties of the galaxy, and you can compare that with what the assumptions are in the analytic model. And so we sort of showed, it's a boring plot, but we showed that the analytic model was failing to do two things. So the basic model just assumed that you retained all of the gas as the galaxy forms, so it didn't account for expulsion in winds. And then even more advanced analytic models that followed it, well, they did account for that, but then they failed to account for the fact that the structure of the gas would reconfigure because you preferentially remove very low entropy gas at the center of the galaxy. So you don't just rescale the galaxy's density profile, it reconfigures into a flatter profile like this rather than this dotted line here. And so the numerical simulations just give you all this for free. This comes out naturally. So this was a really big win that ended up sort of putting me onto looking at X-ray halos for a long time afterwards. And so at that point, they gave me one of these, and I was kicked out. So just for posterity's sake, there's some other characters on here. So this is Raul Angulo, who's still in the field. He now works in Spain. This is Mark Norris, who's up the road at UCLan, is a lecturer there. This is Jim Mullaney, who's at the University of Sheffield. And this guy, Greg, who's a good friend of mine, he ended up leaving the field, and I think he's now head of physics at Rugby, or he was for a while, so he's probably the one making all the money. But yeah, so at that point you think, great, I'm set for life. Where's my permanent academic contract? Well, sadly not. As Indy pointed out, you have to go and graft in astronomy, unfortunately, and go and pay your dues around the world. So unfortunately, learning our craft takes a long time, and we get old quickly. And so 6 years these days as a postdoc is sort of towards the brief end. So I was lucky in one sense. So and it's often sort of assumed that you will move around the world in order to go and get that experience. So I duly relocated myself 10,000 miles to the south in much sunnier climes. So this, for anyone that's been there, will know that this is the Swinburne Centre for Astrophysics and Computing. So we kicked the artists out of their building. And most importantly, all the science doesn't get done up here. It gets done in here, which is the coffee shop, which is run by a Vietnamese guy called Kevin, who has like the most incredible memory of any human being on Earth. I could walk into this place. I've not been there for like 15 years. I could walk in tomorrow and he would know what my order is. The guy's just sort of like a force of nature. So most of the science got done in here. Now, I had a great time in Australia and met loads of really good friends, friends for life. But scientifically, it was a bit of a dead period for me. Australia's still not a particularly welcoming environment for theorists, I think. And scientifically, I struggled there, and my career sort of hit the rocks a little bit. So much so that I even turned to observing, which I'm ashamed of now, but at the time it seemed like a good idea. So. No, I really wanted to grasp this opportunity. So Swinburne used to buy, I think they still do, they used to buy 6 nights a semester from Caltech on these 2 telescopes, which I'm sure most people know are the twin 10-meter Keck telescopes, so arguably the best in the world. And so I thought, right, well, I want a slice of that action. So I turned Observer and put in a couple of observing program proposals and actually got them funded, amazingly. And it almost worked, not for those pesky clouds. So I had a program first on Keck 1 using LRIS to go and get redshifts of gravitationally lensed galaxies found in Hubble imaging. And it went absolutely perfect. So basically because Richard Bauer came and did it for me. But that night was absolutely perfect. And then the second night, sort of a few months later after we'd done the analysis, we were supposed to use laser guide star corrected integral field observations of the best candidates that we'd got, using the Keck 1 data. And the night was just absolute chaos. There was low cloud. They were testing the laser guide star that was newly installed on Keck 1. Subaru was using the laser as well, so there was just like a Star Wars kind of thing going on. There was low cloud, so there was like awful backscattering. We got 2 or 3 shutdowns from Space Command, and I didn't get a single photon. I have an empty CD that they gave me at the end with nothing on. It's like, there's your failure in a CD form. So I decided, after that these critical observations were completely wasted, and there was £200,000 worth of observing time basically down the toilet as a result of that. So the main thing that came out of it was a lot of fun times with Richard. So we also had a run at Magellan, and so this was the post-observing beer on the beach at La Serena. So those are really good times. So despite the failure, I'll cherish those moments. Now, just to give me one last kick on my way out of Australia, I just want to give a word of encouragement to students, if ever you face setbacks. So this was, I think, one of the most important papers that I ever came up with. So this is really Ian and I sort of getting angry with the observational field in X-ray land. Because one of the things we noticed, this was the first time I ever wrote a paper without any simulations in it, and I regretted it. We took all of the data off the archive for X-ray observations of Milky Way-like galaxies, plotted all the properties up, and the blue points here are all late-type galaxies, like the Milky Way, and the red points are all early-type galaxies. And the canonical wisdom was that the X-ray emission was caused by completely different mechanisms in both cases. And we went, are you sure? These things look, remarkably similar. And we wrote a paper about it, and it's still on the archive. You can see it. It's there sort of as a lingering mark of shame. It's got about 16 citations, despite not being published. And yet, literally, as I was going to my leaving do in Australia, I got an email on my phone saying that Monthly Notices had rejected it, which, most people know. Monthly Notices really have to go some way to reject your paper. So we were really shocked by this. This is not a bunch of chances up here. It was sort of like a real kind of, get out of Australia. It just hasn't worked. So fortunately, just before this had happened, hopefully I'm not running too much badly out of time. Just before this had happened, I got one of the most important phone calls of my life. It came in just as I was putting my suit on, actually, like this, to go to an interview at Swinburne for a fellowship to basically remain in Australia. And I was lucky, I already had a fellowship offer to move across to Sydney. I kind of wasn't thrilled about the idea. My career wasn't really going anywhere. And this phone call came in and said, you don't need to go to your interview right now. You should come and work with me. And it was from this guy. And he literally said that. He's like, well, I don't know why you're stressing. You don't need to go to the interview anymore. I was like, I think I'm still going to go. So I'll call you back tomorrow. And he was really annoyed. Okay. But anyway, by the time I put my phone down, I think my heart was already in the Netherlands, where it's remained. I'd already visited Leiden and decided it was the best place on earth. It is a beautiful little city, and if you've not been, you should go. By the time the phone was down, my mind was already off the interview. I did get offered the job, actually, but declined it a couple of days later and duly relocated myself back to Europe. And the reason Joop wanted me to come back was basically to fix all of those problems with Gimmick. So we said, we're going to do this new project. It doesn't have a name yet, but we basically want to make a simulation that gets the mass function correctly, gets all the sizes correctly. Do you want to come and lead it? So yeah. So off I went. So cast your mind back to those two galaxies I showed earlier, because they were basically the key to fixing this. So down here, down at this end of the mass function, we knew we needed to do something differently with the way we treat stellar winds and supernovae. So we put them in a simplified way, but we knew we needed to basically do it in somehow differently, right? So it needed a lot of iteration. And up here, we were forming, far too many really massive galaxies. So we needed some new energy source to go into the simulation, which we knew at the time had to be active galactic nuclei. So we set about coding this up into the model and coming up with, ideas for how to change what we did with supernovae. I went and wrote a big proposal to PRACE, which is the EU network for supercomputing, and we got a big chunk of time on this thing, which was at the time the French national supercomputer that's housed at the French Atomic Energy Agency. So they don't like speaking in languages other than French. So thankfully we had a francophone on the team in the form of Mathieu Schaller, who's Swiss. And they gave us 40 million hours, which we duly burned just trying to come up with the model. So we couldn't actually run the simulations anymore by the time we'd finished calibrating it. So this was long before AI and Gaussian process emulation and doing things in the clever way. We just had to do it manually. And so I ran something like 3,000 simulations to get the right formula. It's basically like baking. And what we came up with was this. So hopefully you'll agree, it looks much better than Eagle. It's not perfect, but it was good enough, and it was better than what the competition came up with at the time. So we were pretty pleased by this. And we would have kept sort of trying to improve this were it not for the fact that we got wind that the competition from, big universities on the east coast of the United States were almost ready to go. In fact, they did beat us. And I had sort of simultaneously the worst and best day of my life when I saw their paper out to start with. Oh no, scooped. And then 3 pages in, oh, that model's rubbish. Shouldn't record that bit. So we knew we were okay. And the galaxies came out looking sensible, right? And this was another big success of the model. We had to put a lot of work into not only getting the mass function right, but making sure that the galaxies came out with the right size. And so as a result, I've kind of condensed 3 years worth of toil here and a lot of swearing and a lot of Renske having to put up with me being very grumpy on a Friday night on the bike ride home because the model still wasn't done. But it was a real sort of formula for success because then the model could be used for, sort of any type of science you wanted. So, another big thing that we did at the time was put all of the data publicly available on an SQL server for people to go and play with. And now the bulk of the papers that have come out of this simulation were written without any involvement of the core team. So that was a really important thing for us to do. So Indy already sort of waxed my car for me, to quote Ian. But I like to sort of show this, and this is slightly out of date now, and I'll have to admit we've fallen off the top 10. But when I made this plot, this was still true. So this is the most highly cited astrophysics papers since 2015. So there's about 250,000 of them, which kind of says there's probably too many astronomers. But if you rank order them by citations, we come out just creeping into the top 10, or at least probably the top 15 now, I think. But what I like to always point out is that this isn't a level playing field. So if you look at what we're up against, so Planck, this is $1 billion project run by the European Space Agency, and you look at the number of co-authors on these papers, there's often up into the hundreds. Well, look, this is another $1 billion experiment. For detecting gravitational waves. So this is LIGO. This plucked out a Nobel Prize in 2017. Half of the world's astronomers are on these papers, and I'm kind of annoyed that I don't get invited. I don't know what I've got to do. Here's another $1 billion mission, Gaia, right? So this has been one of the most successful endeavors in recent years, I would argue. This is very active now, and I think Gaia will end up percolating further up this list. There's AstroPi, which everyone uses these days in astronomy, and then that just leaves us at the end. And there was 22 of us. on the original paper. So it was not a level playing field. I think this was a disproportionate success. And it was because we were in the right place at the right time. I mean, you can't expect this every year. So, if we don't do this again, Indy, please don't get too angry with us. We'll do our best for the next ref. But anyway, we should sort of take the success when it came. So we won an award at the THE Awards. Joop actually turned up late, which was wonderfully ironic for anyone who knows him. So yeah, that was a good night was had by all. So as a result of that, running a bit over time here, sorry. So as a result of that, I got my Royal Society Fellowship, which was probably the most important day of my career, bar this one, of course. Because I knew that was, at that point, I'm probably going to have a career in this field, and I don't have to start thinking about doing something else, because these are sort of a ticket to a permanent job, or at least they were at the time. There's no guarantee these days. And you can take them anywhere, and a lot of people take them to Oxbridge and regret it 5 years down the line. But I wanted to come here, and Ian and Andrea did a lot of, well, they didn't have to do a lot of persuading, but they made the case to me, and it made a lot of sense. I loved Liverpool as a city. I had connections here through family already. And so it didn't take a lot of persuading for me to come here and see if we could start a new group to actually do something fun with all these simulations that we were being involved in. So I won't say too much about what I've been doing in the interim. I just want to pick out a couple of highlights that we've done to show that I think we're still operating at a very high level. So first one of these is e-mosaics. So just to quickly say, globular clusters, for those that don't know what they are, so these are very compact systems of stars, so often up to 1 million or 10 million stars in a very compact arrangement. And you can see these sort of tend to form in the local universe only in these interacting galaxies that produce very extreme gas conditions. And their origin theories are very, very notoriously difficult to test, because you have to basically follow the globular cluster and its host galaxy at the same time, which is very challenging. So when I arrived here, this guy, formerly of these parts, who defected, Nate, he gave a talk about what he wanted to do for his ERC project. So it was actually like a practice interview for his ERC interview. And he articulated this idea that he was going to couple GC formation models to a semi-analytic model. And I was at the back thinking, no, don't do that. So I quickly grabbed him afterwards and said, no, we should do this in a hydro model. So he said, okay, yeah, well, let's do it. So he got the grant, wrote it up, got the grant, and we hired Joel, who most people will know. Sadly, had to go back to Australia. We couldn't keep him here forever. We had 5 years of him, and Joel's an absolutely incredible scientist. I think it's absolutely scandalous the Australians haven't given him a permanent job yet. And we made the first simulations to follow the co-formation and co-evolution of globular cluster populations in a cosmological setting. So this movie shows an individual galaxy forming. So the grey here is showing you the gas, but every dot here is a globular cluster that forms, and it's coloured by how rich it is in heavy elements. And so you can see how globular clusters end up being scattered into the halo of the galaxy, because there's as the progenitors of satellite galaxies come in, it tends to scatter all of these globular clusters out into the wilds of the galaxy. You see there's lots of them here. What's going on is that lots are forming, but lots are also being destroyed at the same time. So most globular clusters are born in environments that are very hostile to their survival. And this all had to be modeled. So it was a real challenge to do this new set of simulations, because the globular clusters have to be followed with time step precision. So every million years you have to update their properties. And so I suggested that Joel made this plot. I'm quite proud that I suggested this, because I think it shows the power of these simulations really nicely. So there are 3 different globular clusters shown over cosmic history here. So this is pretty much the full history of our universe, so nearly 13 billion years shown here. So this yellow system here shows a globular cluster that was born in a very dense environment. And you see very quickly, so the y-axis here is showing you how strongly it's been tidally stripped by its environment. And so very quickly, within like 500 million years, it gets destroyed by these tidal forces. Whereas these two survive to the present day. So this one shown in red, it was born in a fairly low density environment, which is quite uncommon for globular clusters. And it just meanders along and survives, and everything's fine and dandy for it. And this one here, this one was scheduled to end up getting destroyed, but something happened. It got nudged by another galaxy, perhaps, and it ended up being bumped into a low-density environment. So there are many globular clusters that survive because they get bumped in this way. And this had never been shown before, so we were really sort of proud of being able to show this. And we sort of come up with about 30 papers since we created these simulations, and some of them have been very, very highly cited. And I think the key outcome is that we managed to demonstrate that the simplest theory, which is one of the newest, like most GC origin theories are quite exotic and hard to motivate. The simplest theory is the one that passes the most observational tests. So this was a big win for us, and this was all sort of developed in-house here at LJMU, so I was quite proud of that. And the other thing, since he made the effort to come all the way to Weatherby, I'll highlight some work by this guy, so my former student John, who in 2 weeks' time will become my new postdoc. He's coming back from industry. And also in collaboration with Andrew, who, for a brief period was also John's postdoc supervisor down in UCL. So Andrew came up with this ingenious way of modifying the initial conditions of galaxy simulations in a very careful and mathematically rigorous way that you can basically change what's going to happen to a galaxy by making very subtle adjustments to the way it starts out its life. So this shows the power of what that technique does. This is the same galaxy in all three cases. It's the same cosmic environment, but it's just been genetically modified, i.e. tweaked, to form at a different time in cosmic history. And so John really sort of picked up this idea and ran with it when he went down to London. And I think one of the most important results to come out of this is that we showed that most of John's thesis was wrong. Or incomplete at least. So John wrote a couple of very influential papers that have been cited over 100 times, and then he went and undid all of his good work by showing that a lot of the correlations that we show are not causal. There's actually another reason for what's going on. So he was looking at whether or not galaxies develop massive black holes when they form early. And what he showed was that what really helps black holes grow is to have lots of mergers. So galaxies that form early, coincidentally, also tend to have a lot of mergers. And those mergers help to funnel gas onto the black hole in the middle of the galaxy. So this really prompted a rethink of sort of some of our earlier work that I was particularly proud of, using these controlled experiments. So this was really sort of taking the whole idea of experimenting with numerical simulations to the next level. So I'm running out of time a little bit here. So I want to quickly say something about the supercomputing setup here. This has basically been my second job and has caused me many sleepless nights, as I'm sure it has the guys in ITS. I'm really grateful for Kenny and Rick and Mark for coming over to support the lecture. So this is Prospero here, which is the university's centralized HPC facility. So this was basically born out of the ARI outgrowing its own space. So back when I arrived, Ian and Andrea had already started building up a small HPC facility here, not for running simulations as such, but for analyzing those that we ran on bigger facilities elsewhere. And then sort of about, I'd say, 7 or 8 years ago, coincidentally, Ian got his ERC grant, which came with a huge amount of money, and I got a big Royal Society grant through as well. And so we were both coincidentally had a big chunk of change, and we wanted to make a step change growth in the size of the machine that we were able to buy. And the big problem was we couldn't put that in the ARI. We didn't have any of the infrastructure that was needed to build a system of that size. So ITS stepped in and allowed us to put it in the university's main data center, which is just sort of over there, over that way, on this campus. And the problem is we've kind of now outgrown that as well. So Prospero was born, I always like to think, August 2020. So Mark actually sent me a message saying it's switched on just as Renska was going into labour with our first child. So in a way I had 2 kids at once. Well, I didn't. But, so it started off with 20 compute nodes, which was, these are very high density nodes, so 1,300 compute cores with 11 terabytes of memory, by which I mean RAM, not storage. And we bought a 1.5 petabyte parallel file store, which has been nothing but trouble ever since. And the nice thing is that we've been able to invest more and more in this system. So it's now up to 52 nodes, and that money has come from various sources, but a large chunk of it has come from the RCIF allocation that's come into FET. So I'm very grateful to Indy and Jin, who have been very supportive of this endeavour and funneled money into this. So it's now up to 28 terabytes of memory, and more importantly, I think it's the number of users that are on it. So it started out as just a bit of an ARI thing, but now there's people from all across, not only our faculty, but also the other faculties as well. So I think this is a success story for the future. It's not where I'd like it to be. I think we've got many problems to overcome still, chief of which is staffing. We don't have enough people to support it. So this thing runs through the benevolence of staff in IT and me putting in a few late nights as well. But it's doing a great job for us, and I think going forwards it's going to be a very important research facility for the whole university. So I'm hoping that this is going to keep going from strength to strength, and we'll find a solution to our accommodation and power and cooling problems in due course. But the key thing I would say about it is that it's available to everyone. It was designed from the ground up to be a facility for everyone in the research community to use. So everyone is welcome to use it. Okay, and I'll name and shame them and say, I'm sorry, Rick, I should have put you on here as well. But here's Mark doing his impression of Planet of the Apes, and there's Kenny looking very dapper. So thank you to these guys who field far more emails from me than they should have to expect to do so. Now, I just want to say one thing about exciting results to be born specifically out of the HPC facility. So, I mean, obviously, the simulators like myself and In and Andrea and all of our group use the machine a lot, but it's most sort of gratifying to me that there are other people who will use it, chief of whom was someone who sits across the dinner table from me most nights. So I think one of the most exciting results to come out of it is Rentger works on JWST, and the redshifts for these these are the four most distant objects known to science, known to mankind at the moment. So this one's at a redshift of 13, and it was Rentger and her postdoc Joris, who works down in Cambridge, who first came up with these redshifts, and they did it using Prospero. They didn't use Cambridge's machine or Arizona's machine. They did it on our machine because we were nimble and we were ready to go with the blink of an eye, and we got everything installed on the machine, and Kenny helped us with that. And so this number, which is a very important number in the field of extragalactic astronomy, was come up with on Prospero. So that was really exciting to me that's where it was done. So I've been speaking for far too long now, and I'm starting to enjoy myself too much. So I'll sort of try to bring things to a close. So I want to just quickly say something about recent milestones that I'm quite proud of. So I'm sorry this is a bit conceited, but I've managed to sneak into the highly cited researchers, not consecutive years, but in alternate years. We won the Royal Astronomical Society's Group Award for Eagle in 2022, which is really nice. If you look at the other teams who have won that thing, it's kind of people like Planck and LIGO that tend to get it. So it was nice that we crept in. I wrote this review last year that had cost a lot of sleepless nights and a lot of toil. It lasted for 3 years. I lost my first co-author and killed them off. I had to rely on an old friend from Leiden, so thankfully Freke van der Voort from Cardiff stepped into the breach at the last minute and basically blitzed it. Without her, I would never have got it done. The last sort of 6 years I've been involved with Dirac, so not only as a user but on the resource allocation committee. So in the last 3 years I've sort of stepped up into roles of greater responsibility. So I had 2 years as deputy chair and 1 year of chair, and thankfully that's over. So I'm quite proud. This year we allocated £30 million worth of resources, so it's a big deal for a relatively small panel, which is mostly made up of quite early career researchers. And you do get some pretty hairy emails from senior people when they don't get what they want. Now, it had nothing to do with me being chair, in fact, quite the opposite, but a big chunk of that 30 million actually came to our team this year. So 8 million came into Virgo UK, and a big chunk of Virgo UK is LJMU. We're now the second largest node of Virgo UK. So, a big chunk of that time is coming here. And then recently, I've mentioned that John's coming back as a postdoc. So that was enabled by one of these new SGFC Small Awards. This is £500,000 of funding over 3 years that came in towards the end of last year. So I'm really excited about what we're going to be doing with that money. And it's great that John's agreed to come back and fill that post. So I just wanted to say I don't always get such brightly coloured robes. So I did a PhD defence in Leiden earlier this year and got this much more sombre get-up. So this isn't Evgeny, but he did look like that by the time we finished with him. So I did wear the hat on that occasion. And just finally, right, astronomy's a team sport. It's not at all an individual sport. And I'm very lucky to have a lovely group of people. And I say that with great sincerity. I'm not mocking you. So this was taken a week ago with this lovely group of people. So I'll put their names up here. So thank you to you all for coming along. Andrew and Emily are sort of on loan. I only co-supervise them, but it doesn't mean I love you any less. And I'll just, even though he's here, so I'll put John up there. That's about the right dimensions. And I couldn't finish without putting these characters up. So these are my former charges. So Adrian and Alex were both PhD students in my group. So thanks to Alex for coming along. Adrian's now in the States, causing trouble there. And Oliver was a postdoc for a few months, and we're still sort of working on a paper. He's now over in Poland, working at the Warsaw Centre for Theoretical Physics. And a quick final thought, right? So I guess now I'm a professor, I get to profess. So I'll make a quick statement, which I hope will be reassuring to youngsters. So I used to be very intimidated by senior academics who, when they would tell the story of their career in the way that I'm now able to do, they would frame it as having been carefully planned from the outset. And it's not until you get old and grizzled like me that you realise that these people are just lying. Because you can't do it. No one knows what the future holds. So when I hear statements like this, I always kind of roll my eyes. I got into this game to do X, Y, and Z, and 20 years later I got to the answer. Like, no one does that. I don't believe it. So it was a great reassurance to me. I watched Jim Peebles' 2019 Nobel Prize lecture recently, and I'll wax my own card. Jim Peebles is somebody I've had a conversation with before, which obviously made me cleverer by osmosis. He gave me some advice which I studiously ignored. He told me to work on dark energy. I said, no. But he said something really nice that resonated with me in his 2019 lecture about how he got into doing all of the things that won him a Nobel Prize. And he said, I could see a few things to do. That led to a few more things to do, and that carried me through my career. And I think that couldn't sort of sum up what I've been doing any better. Like, I've been lucky to fall into good projects, not always through judgment, but through luck, really. Now, I should say that, Jim's things to do are unquestionably loftier than mine, which is why he has a Nobel Prize. But I do feel better knowing that I'm not the only one who didn't plan it all from day one. If he can do it, I think it's good enough for him, it's good enough for me. So that's my final thought. My final statement I shall reserve for this cast of characters. So, oh God, compose yourself. So everything I do, I am very lucky that there's a very tolerant person behind me. So Renska's, world-class astronomer, trying to, do her, get her career going as well, or to keep it going. And she disproportionately takes a lot of the hard work at home. I do try, but I have to admit that Renska does more than I do, particularly when it comes to controlling these two, who are the love of our life, but often give me more and more of this stuff. So I couldn't do it without you, Renska. Thank you very much. And I'll finish there. Thank you all very much for coming.